Okay, so we now need to consider that this body now being pulled down a distance of 25 centimeters and released. So if we look at the diagram I've sketched here, you've got the natural position of the spring, which is 0.5 meters, 50 centimeters. But if, of course, a weight is placed on the end of the body, there's going to be a stretch due to gravity. And we worked out in the first video that that was 15 centimeters. Okay, so that's its natural equilibrium, if you like, right? That's the natural length of the spring. But when a particle is attached to it, this would be the natural equilibrium. Okay, so we can put in inverted commas there, natural, in the sense that it's natural when the body's attached to it and gravity is affecting it there. Okay, and then it gets pulled down a further 25 centimeters down here and then gets released. So what happens is then when it gets released, it will perform SHM about the equilibrium position there. So the equilibrium position will be the mean, okay, point, not the natural. It won't be that natural position, because this is what we want to think of, if you like, as the natural position due to gravity. Yeah, that's our natural equilibrium. Okay, so it gets stretched 25 centimeters down, released, and then it performs SHM about there. Okay, and it's okay for the spring to go higher, to go into this natural length, because what will happen is there'll be a compression with the spring then when you go less than the natural length. Okay, and it'll push it back down. So we'll have SHM. Well, we're hoping we'll have SHM. We're going to prove it now mathematically. Okay, so what you want to do, right, we don't want to consider it when it's stretched there, okay, when it's been pulled down and held at rest, because it's not performing SHM. We need to see when it's moving. So we need to consider, okay, body as it is moving in direction of increasing x. So if we measure x from our natural sort of equilibrium position there, our mean point, so we measure x going that way, it's positive. This is our increasing direction. So if you think of the forces then, when we apply Newton's second law, okay, well, this way is positive. We have actually got a force, haven't we, going this way this time, because the weight, isn't it? The weight is going to be 6g. But of course then you've got the opposing force, the tension in that spring T. So applying Newton's second law, you've got the 6g pulling it down, but then you've got the resistance then of the tension pulling it back, and that will equal to the mass then, which is 6 times the acceleration. So there's Newton's second law there, okay? But then we know how to work out tension, don't we? Remember, tension now can be worked out using Hooke's law, yeah? Now tension is not going to be the same as we had in the previous video, because remember the tension straight away in the previous video we worked out to be 6g. That's only the case when it's in equilibrium, okay, when it's balanced. But when it's moving, that spring is going to be stretched even more, so tension in effect is going to increase, is it? As that spring gets stretched, the tension is going to get bigger and bigger, and it's going to be a lot more than 6g, okay? It's going to be more than 6g as the spring gets longer and it's stretched, and it's obviously got to be more because it wants to put it back into that equilibrium position there, yeah? So we can actually work out the tension by Hooke's law. So T equals to lambda, okay? Now let's think about what the extension is. We've got to be really careful here, right? Because using the formula lambda x over L, yeah? Now the extension in this case, yes, it's x from the equilibrium, but remember the actual extension in Hooke's law is from the natural position of the spring. Okay, so we don't just want to consider the x distance here for the extension of the spring, it's actually all of that distance, yeah, because the extension we're referring to in Hooke's law is about the extension of the spring from its natural length. So it's been stretched 0.15 plus x, okay? So that's what we want to put there, over then the natural length. So we can fill them in, can't we? We know lambda is, what was it, 20g, wasn't it? okay? And we know the lateral length was 0.5. So we've got that. If we sub it back in here, so if we call that star, okay, we'll have 6g take away 20g 0.15 plus x over 0.5 equals 6x double dot. Now what I would do here, I would divide these. It just makes it so much easier. 20 divided by 0.5. Do that first. 20 divided by 0.5 is 40. Before you multiply out the bracket. Or you could times through by 0.5. That's another way of doing it. Times through the whole thing by 0.5. Your choice. I prefer to do that. So you get 40g there. Multiply out. So 6g minus. Now, if I do 40g times 0.15, you actually get 6g. And then minus 40g times x is minus 40g x equals to 6x double dot. Okay, so the 6g's cancel. Okay, which is quite nice. And we're left with minus 40gx equals 6x double dot. So we can then work this out. So minus 40g is 9.8. And then divide by that 6. So take the 6 over. And that'll equal to x double dot. So my calculator, let's work that out. 40 divided by 6 times 9.8. Okay, so 40 times 9.8 divided by 6, and I get 196 over 3. Okay, it's not particularly nice. Minus there. So that will equal to x double dot. But you've got SHM. If you notice that is SHM. So basically, this implies SHM. So motion is SHM since it's of the form x double dot equals minus omega squared x. Omega then will be the root of this. So the root of 196 over 3, okay, which will equal to, well, you can put in your calculator if you want, but that comes out to be 14 over root 3, okay, or rationalize it on your calculator, whichever way. So that's your omega in that case there. But we've definitely got SHM, as you can see.